So, welcome to this webinar that we call Solvents for Reduced Environmental Impact. Maybe someone else can let people in, since I only have two screens, so it's difficult.
We will.
Yeah, good. See if I can also change to picture number 2, that this will be recorded, and number 3. So the agenda looks like this. We have 1.5 hours to tell you about our project BioCleanPaint, where we have investigated this, the theme of the day, so to say. So we start with some brief background, purpose and goal, and who is participating in the work, who have been participating. And then we will get an overview of the process map of the washing liquids at Scania. And then we will go through some methods and results, and both lab scale tests and pilot scale tests, and then the LCA, life cycle assessment, that we have been doing. And then at the end, some questions and discussion time for that, at least 10 minutes. So 1.5 hours, and we have an internal agenda with time slots, but that we will not reveal. But we think we will be fine with 1.5 hours. So welcome, everyone. So I am then Charlotte Ireholm. I work here at RISE, and I have been the project leader for this research project that we call BioCleanPaint. And this is where we have investigated this. The goal with this project has been to investigate how we can how the climate impact from using solvents in the washing liquids for painting in paint shops, how that can be reduced by either use non-fossil based solvents, and scenario 2 then, how can we impact the climate impact by using recycled solvents, and what type of techniques are there to do that at this stage in Sweden. So it's been a project that started in November 2021 and will end now at the end of September 2024. And the project team, the project partners that have participated is, except us from RISE, me and several colleagues, it's the end users, so to say, the companies with their own paint shops. So Scania, Saab, and Volvo, and also Provexa and Yta. And then we have also in the consortium then Circum, which are doing recycling of solvents, and we have Stena Recycling and Envirostrip also. And this is a project financed by FFI, fordons strategisk forskning och innovation. Yes, and with that, I will leave the word to our next presenter, which is Martin Jönsson from Scania, who will tell us about the setup, or what is it that we have been looking at. What is washing liquids from Scania perspectives, to give you a good background of the project setup, so to say. So Martin.
Thank you. And now I see the font is a little mixed up here, but
I see that too.
Yeah, hopefully you can read it anyhow. Yeah, my name is Martin Jönsson. I work down here at Scania Oskarshamn. And at Scania Oskarshamn, if you have the next slide there, Charlotte, one more. We manufacture cabs for the Scania trucks for 3 production units in Europe for Södertälje, Zwolle and Alger. And the production rate here is around 350 cabs per day. And we produce these cabs then with all of the interior included in the cab. So it's with the seat, with the steering wheel, dashboard and everything. So it's just to dock the cab, so to speak, to the rest of the truck at then Zwolle, Alger or Södertälje. So take the next slide. And here, of course, we then paint the cabs. And here at Oskarshamn, we have 3 different painting lines. If you take one forward, Charlotte. We have 2 that is water-based, where we have the main part of the trucks going through the BCA and BCM painting lines. Here we use a rinse solution together with water to clean the paint system. Because we have in our portfolio, we have around 450 different colors that we paint the trucks with. Now we mostly paint the trucks with the color white, because that's what the customers want, around 50%. But the rest of the trucks then can be of different colors. And the main part of these different colors, one could say, where we have a lot of mixing, is in this CCM line, and it stands for clear coat manual line, where we have a solvent with the solvent-based colors running through here. And here we used thinner as the cleaning agent then for this line. And we can take the next slide, I think. And if we look at the other production unit for Scania, we of course use always solvent-based paint also here. We have a production unit in Sao Paulo in Brazil, and we have a unit in Meppel in Holland, where we paint the polymer parts for the chassis. Here in Holland, we use a lot of solvent-borne paint. And as you can see here, is that even though we paint with the same basic paint material, we have some difference, of course, with the paint material, but this, rather much the same. We have different compositions of the thinner. This is rather interesting. Thinner is apparently a name for the compound, and it doesn't really say what kind of solvents it's including in thinner. If we take the next slide there. So here is the CCM, the clear coat line that we have here in Oskarshamn, schematic diagram over the line. And we have virgin thinner then coming in, clean thinner that cleans the painting robot and cleaning of the piping systems. And of course, this is a rather long way from the paint kitchen where we load the paint down to the actual paint robot. So it's rather much hoses that needs to be cleaned. If you take the next slide.
Yes.
And between every color shift, we use around 12 liters of virgin thinner then to clean the painting systems. And one can say the thinner is consumed or for a better word, but consumed in 3 different ways, one could say. A part of the thinner is going from the color block to the painting gun, is going down in the water treatment, but this is only a small amount. The main part of the thinner is going through all of the paint system and cleans all the way the paint system from the paint kitchen down through the paint robot here, one could say, and it ends up in this container then with dirty thinner. And this is then of course also mixed with a bit of paint residues. And it should be remembered here also that as it's solvent paint, of course the paint residues will also contain some solvents from the paint, will end up in different solvents from that we have in the thinner from the beginning. And also small part is going away in evaporation in the process of course. We will see a bit on the calculation here on the LCA further. If we take the next slide. So if we look at 2021, we used around 140,000 kilos of thinner, virgin thinner, then that's around equal to 3 cubic meters per week. That is used in this process then. And as you can see also, we use this EBC container, so it's on 1 cubic meters in the containers. We don't have any bigger tanks for this, so it's rather much handling with these EBCs. If you take the next slide there. So this the used thinner then that we have that is used only once is today sent as waste to be burnt at the waste treatment company actually. And even though it's a resource, we have to pay money to get rid of this waste. And also this waste then influence our KPI, our amount of waste that we have on each cab, that we of course collect data how much waste we have per cab, and this waste then ends up to be around 1.5 to 2 kilos per cab.
We have a hand raised for a question. I think it's okay, right? Or should
Yeah.
So Thomas.
Okay, thanks Charlotte. Hi Johnson, that's Tom Idle from MN Truck and Bus in Munich. One question, CCM stands for what? Clear coat manual or
clear coat manual, but it's not really manual anymore. It's its old name. It's more automatic now than manual, the line.
Okay, and you need how many liters? 12 liters per I think the slide before or 2 slides before.
Yeah, around 12 liters to purge the systems.
Okay, how many robots do you have?
Hard question. I think we have Jimmy with us. He knows this stuff. Jimmy, do you know?
Okay. Yeah, on the CCM line we only have 2 robots, but they're fairly old ones. It takes quite a lot to purge the system. It's two robots, and then there's 2 guns as well because it's a semi-automatic system.
Okay, my question is, I just try to compare these values with here with our cab manufacturing in Munich. And we don't have a base coat clear coat system, only for metallics. So it seems a lot of amount of solvents.
It is a fairly substantial amount of solvents, yes. But as I said, it's an old system with fairly old technology, so it's unfortunately not much we can do to reduce the amount as it is right now.
How old is it?
Oh,
good
can't remember, but it's 10 years, maybe 11 years.
Okay,
I'd say so. So it's fairly old.
Okay, because here in Munich we started in 1982 with our production line for cabs. for pre-treatment, e-coating, and so on.
Yeah.
And then in 2018, we started with the new paint shop. Some guys of Scania, they know it. They have been here.
Yep.
So, and in the old paint shop, we still have 2 top coat lines. There's one with a 1K system and a 2K system. And the 2K system is or low bake actually. So and there is only a clear coat there. But I think the amount of solvent is much higher than we have here in Munich, just from the values. So this is the reason why I ask for.
Yeah, maybe something we could compare notes on, but I'm not sure how they built the system because I wasn't there when they built it. I only know the current usage numbers.
Okay, but anyway, maybe we can come back later on that or after the session. Thanks.
Yeah. Thank you very much. That was my last slide, I think.
Let's see what comes next. Yes,
Yeah.
that was the last.
Yeah.
Thank you, Martin. Actually, so then you have the background. You know what it's this thinner volumes that we are looking at or have been looking at in the project. So we will let the word to my colleague Mikael Kjellin, who is going to tell you about a substitution tool where we look at alternative solvents and some overview of the lab scale tests that we have been doing. So
Thank you very much. I'm going to try to take control over the presentation.
Good.
And I think it takes some while, but I'm going to start to describe our so-called substitution tool to find alternative solvents, and then describe what we have done in this project. So it appears that I cannot change the slide.
We thought we were smart so that we only had one, didn't have to change who is sharing, but maybe. Now you have control.
Do you see my arrow?
Yes,
yeah.
Yes.
Very good, very good.
Okay.
So in principle, it builds on the chemical principle that like dissolves like. So if you want to dissolve a non-polar active, you need to use a non-polar solvent, and if you want to dissolve a polar substance, you want to have a polar solvent. So I'm still trying to change the slide.
I will press and see if what happens.
Yeah, maybe you can change the slide.
Yeah. Okay. Yeah.
So it slowly changes the slide. So we basically use the Hansen solubility parameters, and Hansen defined 3 parameters that sort of describes the type of interactions that can occur between molecules, because that's actually what determines the solubility power of the solvent. So one factor is our dispersion forces, which is sort of an interaction between non-polar molecules. And then we have polar forces, which is interaction between dipole or dipole induced dipole. And then the third one is hydrogen bond forces, which is considered as like an electron acceptor donor type of force, because all molecules doesn't have a hydrogen, but they're present in the Hansen space. So if you have these 3 different parameters, it's possible to define the so-called Hansen space, and then each chemical substance can be placed in this Hansen space, depending on the values of the dispersion forces, hydrogen forces, and polar forces. And I just placed a few of these solvents here: acetone, ethyl lactate, hexane, and ethanol. Ethanol is more polar, so it's closer to the water. And if solvents are close to each other in the Hansen space, in principle, they mean that they are soluble. And already here you can see a problem with water. Water is it's a very special substance, and it's very far away by itself in the Hansen space, which means that it basically should be non-soluble in any solvent. But it really shows that you cannot use this Hansen solubility parameters really if there's a lot of water in the system. If there's a little amount of water, maybe you can use it. you can consider water like it bonds like trimers or dimers. So I'm going to change the slide, or maybe you do it. You still have some control, actually. Okay.
Yeah.
So
obviously.
how does it look for a polymer? So a polymer can also be placed in the Hansen space, but besides the actual location, the coordinates of the polymer, you also have you define a radius. So there are actually spheres lying in the Hansen space, and if a solvent is located within this sphere, it's soluble, and if it's located outside of the sphere, that solvent cannot dissolve the polymer. So, for example, this red solvent cannot dissolve any of these two polymers. If it's located towards the edge of the sphere, it's a good solvent, medium, yeah. But if it's located close to the coordinate of the sphere of the polymer, it's the best solvent. So the distance in the Hansen space between the polymer and the solvent gives the predicting solubilizing power of the solvent. So next slide, please. So how do you determine the Hansen position of a solid material? Well, basically you have your polymer and you cut it in small pieces. And then you put these small pieces in many different solvents. We usually have maybe 30 solvents. And then measure how does the polymer look like after some time, 1 hour or 2 hours or 1 day or even longer. So this can be a long process. So for example, polymer 2 here, you can see some substantial swelling already actually after 1-2 hours, whereas the interaction is much lower for polymer 1. So what you just do is that you determine, does it swell or not? If it's non-interacting, non-swelling, you just say it's 0, and if it's interacting, you say it's a 1. And then you use the HSPIP Hansen program, and you just enter the 1 or the 0 in the program, and out comes the Hansen parameters and the Hansen sphere, the radius of the sphere. And maybe I'm let it sound too easy, I just do it, but it can be difficult because, for example, for this polymer 1, is it interacting or not? Clearly, there's some swelling, but it's of course much lower swelling than polymer 2. So polymer 2 is sort of more soluble in this particular solvent than polymer 1, and this can be a bit tricky. So next slide, please. So how do you find these Hansen parameters? So you can find it in literature, or you can find the software which you can buy. It's maybe, I don't know, maybe 1,000 euros, but then you have like a lifetime license. So it's not very super expensive. So the software contains the Hansen parameters of many different solvents and the cast numbers. There's also a possibility to use the smiles of the solvent to get a value for the Hansen parameters. And the lab tests I have already described. So next slide, please. So then you can actually have you can rank solvents with the solubilizing power, but there are many different aspects of the solvent that are important, of course, if you can use it. So, and you have to consider the physical and chemical properties of the solvent, like, for example, melting point, viscosity, evaporation rate, and odor. And that's actually where the rise substitution tool comes into place. So from the Hansen program, you get like a ranking of the solvents with the solubilizing power. And then with a substitution tool, you filter with these physical and chemical properties. So you actually get fewer and fewer solvents that are possible, and then you can make an assessment which solvent you can use. So next slide, please. So this is just a little example called Xylean. From the Hansen program, it's loaded with thousands of the solvents. So some of them, of course, you can take away immediately if they're chlorinated or brominated or something like that. But in principle, from the program, you get the distance in the Hansen space from xylen, if the xylen is what you want to replace. So the distance xylen to xylen is of course 0, and then there's a decreasing matching, sort of a, well, increasing distance in Hansen space. And then from this list, then you just filter out on the relevant parameters that are important to you, if it's evaporation rate or if it's a boiling point or melting point. And then we have a database, well, that we have put in many the toxicology of many substances and also older, and we have like a system for the price. It can be difficult, of course, to get the price, but we have a system to get that to just to, yeah, like a brief assessment of it. So this was the alternatives to xylene. So we identified 2, so pentyl acetate and propyl acetate. And pentyl acetate is closest in price and lowest price, but it has a little higher aquatic toxicity than propyl acetate. So next slide, please. Okay, and the program is it's also possible to use solvent mixtures in the program. So if you want to solubilize a polymer, that this red one, and you have you want to use 2 solvents or 3 solvents, those are defined. You can make a mixture of these 2 or more solvents, and what you do is you calculate the Hansen parameter of the solvent mixture, and you make the mixture be as close as possible to the material that you want to solubilize in the Hansen space. So if you have solvent 1 here and solvent 2 with the yellow, the 50-50 mix will be in between. And yeah, in this simple example, it also minimizes the distance to the materials you want to solubilize. Next slide, please. So going over a little bit to the BioCleanPaint project, Charlotte, please tell me when the time is running out. But no I forgot to take the time as usual.
That's fine.
So the solvents that we have used that are used in the factories in this project are these 6 to the left. So butyl acetate, ethyl acetate, xylen, ethylbenzene, and 1-butanol and ethanol. So we just plotted them in the Hansen space, and these 2 very non-polar substances is located here in the left corner. And then you have the 2 alcohols are to the right, and the esters are sort of in the middle. And the solvent 1 and 2, it consists of xylen, ethylbenzene, N-butyl acetate, and 1-butanol. Solvent 3 consists of ethyl acetate and 15% ethanol. And basically all, as I will show, all solvents are quite close to each other in the Hansen space. And just you can look in literature if are these solvents recommended or not. I mean, in this project was about using bio-based solvents, and I think that and the price is of course important. So ethanol and ethyl acetate can be made totally, and that's available, so 100% bio-based. But I think you can produce, I mean, through of course more complicated things or reactions, you can produce maybe whatever you want from biomaterials, but yeah, ethanol and ethyl acetate is sort of a low-hanging fruit here. And xylen is listed in this Chem 21 solvent guide as problematic. Ethylbenzene was not part of the solvent guide, but it's probably as problematic as xylen, judging from the MSDS. So it's I mean, like toxic and everything like that. So the most important thing is to sort of get rid of the xylen and ethylbenzene. So next slide, please.
One comment then, Mikael. What you call here solvent 1 and 2 and 3 is the thinner mix 1 and 2 and 3, right? So if you compare to Martin's presentation, he used a thinner, which is a mix of solvents. So solvent 1 here, that says solvent 1 is several solvents in a mix.
Yes.
So solvent mix 1.
So thinner 1 and thinner 2 consists of xylen.
Let's see.
Next slide, please. Yep. So we started then looking at the different paints and also the different, the hardeners, the curing agents. So assessing the Hansen parameters of the paints. And basically then these are the different paints. So polyurethane, acrylic paint, and there's a paint 1 and paint 2, and solvent 1 and solvent 2 are used for those two. And paint 3, cured epoxy, and the solvent 3 is used for that. These are the different solvents that we commonly use when we assess the Hansen parameters. So we take 2 milliliters of each of these solvents in small vials like this, and then I put the paint or the paint ingredients in these little vials. I shake and then see if it's dispersible, or is the glass clean, or does the paint stick to the does the phase separate stick to the glass? And then if it did that, it is a 0, so it's non-dispersible, or lots of depositions on the glass, bad cleaning effect. So I put this in the Hansen program, the 1 and the 0, and out comes the Hansen parameters of the different materials. So just an example, this would be then, you can see a phase separation here. The paint is in the bottom and some on the glass. That would be a 0. Here you have a totally dispersed paint, the 1 here. And this is then the judgment of different. Next slide, please.
Yes.
So this is how it looks from the Hansen software. The score is the 1 and the 0, as I said, and then you press this calculator, and this is the output. What you get there is the coordinates of the paint, and then the solvents that are inside the calculated sphere are the blue ones, and the solvents that are outside of the sphere are red. So this was quite a good fit, because what can happen is that, because it can be difficult to define 1 or 0, so it can be the case that you have solvents inside the sphere which did not dissolve the paint. So then it would be a wrong inside, or it can be solvent that are outside of the sphere but actually did clean or did disperse the paint. So then it would be a wrong outside. But in this case, there are 0 wrong in and 0 wrong out. I think there's a problem with the font here, but to the right you have the Hansen parameters of the different paints. So I can only see paint 1 and paint 2, but there is a paint 3 as well in the presentation.
Should I go to?
Yeah, it's not super important. Yeah. You could actually change. That's very good. Okay. So next slide, please. Good. Okay, so these are the different paints. I can mention that the different ingredients of the paint, like hardener or the paint or the curing agent, those had similar Hansen parameters, which is natural since they're soluble in each other. So these are just for the paints, which then are the curing and the thickener activators mixed with the paint. So they are located quite close to each other, and the different solvents are also located quite close to each other. So for paint 1, for example, you can see this is the sphere, and all of the different solvents, the thinners or the solvent 3, which is ethyl acetate and ethanol, they are inside the paint sphere, and they could solubilize the paint. And what you can do in the program is that you get this relative energy difference, RED value, and that's an important value in the Hansen. If it's 1, then it's located on the perimeter of the sphere. If it's below 1, it's located inside the sphere, and if it's above 1, it's located outside the sphere. And these solvents are located inside the sphere for paint 1, and that means that the RED is below 1. Okay, you know this, solvent 1 and 2 consists of xylen, and solvent 3 is ethyl acetate methanol. So based on the Hansen parameters of the paints, we could use the substitution tool to identify different solvents, of course, if it's possible. 3 examples are dimethyl carbonate, ethyl lactate, and anisole. But this is sort of based on thermodynamics, and kinetics is something else. So you really need to evaluate how efficient these solvents are to the paint. And that's the next slide. So we identified many different solvents, and we did sort of a rapid screening of the solvents to be as efficient as possible. And what we do is that we make a 60 micrometer paint film. We have a glass slide, which is a glass surface that is maybe 0.5 meter, and then we make a long paint film, and then let it dry. And then we could have prepared different solvents, and we could sort of drop solvents all there, and then after here, and then also filming all the time, so we could see the solubilization effect. And yeah, what you, for example, could see, one is the width of the track. So we drop the solvent here, and it slides down because it's tilted. So if it's very broad, it's actually a measure of the surface tension. So if the surface tension of the solvent is very low, we get a good wetting and a good sort of a broad track. But that doesn't mean that it sort of makes it clear that it can take away all the paint where you drop here. So it's just, yeah, different effects. For example, ethyl lactate here, Hansen showed it would be good. But yeah, it does solubilize the paint, of course. I mean, if you drop water over this film, it will not solubilize anything. So it does, of course, solubilizing, but it's not as efficient as, for example, isobutyl acetate. This is solvent 3, really good and efficient. Solvent 2, which is for this paint, and it's not as efficient as solvent 3 in this test, at least. Yeah, and when also what you can note is that solvent 2 consists of xylen, ethylbenzene, and butyl acetate and butanol. But if you just evaluated butyl acetate and butanol mixtures, we could see that it's almost as efficient as this solvent 2. So one possibility is to use butyl acetate and butanol. It might be a lower sort of a threshold to change in the factory to butyl acetate and butanol than to a completely different solvent. So just taking away 2 solvents might be a more better option. Xylen by itself wasn't super efficient. But okay, next slide. So yeah, so we sort of focused on these ester alcohol mixtures because they seem to be very efficient. And I tried to show here the solvent 1 and solvent 2, that those are the thinner 1 and thinner 2. So there are xylen in there. And then you have the butyl acetate and ethyl acetate, and then the 2 alcohols. So you can see that the butyl acetate and ethyl acetate, they're quite close to the thinner 1 and thinner 2. So it should be possible to replace these 2 salt thinners by these ethyl acetate ethanol mixture. Next slide, please. And this shows an example of what we did. So this we have taken microscope slides. So they're quite broad, and we got an applicator that we can use on these broad microscope glass slides. So it's quite a good test. This is the paint film. We mount it. We mount it tilted, and then we drop the material, the solvent here, and then we get to sort of a profiles. And here, this is to the left, there is 100% ethyl acetate, and to the right, it's 100% ethanol. And then in between, there are different mixtures. So solvent 3 is this 85 to 15 mixture of ethyl acetate and ethanol, and it's quite efficient. We measure how much it takes to break through the paint to the glass. And these are dried film, and what you can see is actually you get this very thin layer of particles, which are, if you just touch this surface, the particles comes off. But it was actually, when you dry and take this picture, you can see these particles. But we noted here that we actually could use a 50-50% mixture of ethyl acetate and still have a very good effect. If you have too much ethanol, it's not very efficient. And also, actually, if you have only ethyl acetate, there's some kind of a phase separation here. So you need some alcohol to get a good effect. And I remember now that I can also say that, okay, this is a very this shows the chemistry of the paint removal. So, I mean, of course, if you have a mechanical effect as well, then it's possible that this 30 to 70 mixture would be okay if you have also a mechanical effect of the spray, then you add to the cleaning effect. Okay, next slide, please. So also important is to look at the different materials that the solvents come into contact with. So we collected the different materials from the factories, like you have the plugs, you have the O-rings, you have the tubes, and then we cut these materials in little pieces and put in the different solvents that we use to calculate the Hansen parameters. And measure then the weight increase after 2 weeks. So for 3 of the solvents, it was complete solubilization. So, for example, solvent 2 and solvent 7, you can see that it just has dissolved entirely the piece, the plastic part. I use that as a criterion for the Hansen parameter. So if it's above this line, above 250% increase, I had a 1, and then if it's below, it is 0. And then I got, since I had this very a tough criterion, I get this very good fit and very good definition. If I would have included these 2, I can't remember how, but it probably, the sphere would have been much larger, and we could get like an wrong in or wrong out. But the center point of the material doesn't change that much actually when you do this. So now we know the Hansen parameter of this blue material, and then we can calculate the relative energy difference to solvent 2 and 3 and 1, and we get larger than 1, which means that the solvents does not solubilize this blue material and should be compatible. But the solvent 1 and CO2 and solvent 3 is the 18, 19, and 20. And you can see that also for these 2, you have some sort of a weight increase, actually. So I think the conclusion is that, yeah, you can get a good indication from the Hansen, the distances in the Hansen space between the polymer and the different solvent that we use. But I think this is a good way to verify it experimentally, that you need to, you cannot trust the Hansen assessment really. Maybe you can show next slide. Then I have some more materials that I put in. So the blue one, that's what I showed in the previous slide. And then you have materials that are very non-interacting with the different solvents. So it's very difficult. I mean, there are fluorine-based O-rings and fluorine-based tubes, and you get very low interaction. Then it's of course difficult to calculate the Hansen's coordinates. But so I think that the general message here is that you need to just verify it experimentally if it's okay to use a solvent with a material. I think you cannot come away from that. Yeah, and I think actually that was my last slide. So I mean, within this project, we then have identified different solvents that can be used. So you can use, for example, butyl acetate and butanol, and you can use ethyl acetate and ethanol. Very efficient. And then also other solvents can be used. But yeah, so there's like a toolbox of different solvents now that we have identified that can be used as a replacement for these solvent 1 and solvent 2.
Any questions to Mikael before we continue? with some pilot scale or higher volume lab scale tests that we have been doing then to also verify or control if the small lab scale test where Mikael put some droplets on the paint, how soluble the paint is with the different solvents or thinners. So we have our pilot scale lab setup here at RISE in Måndagen. So it's a pump, a spray application with a small pump. So it's it's not at all what you have at Scania in Oskarshamn, but at least something in between, one step further. So with quite a few meters of hoses at least. So the idea was then, or the procedure that we did, was that we filled the system then and pumped through 3 deciliters of paint through the system, and the hose, even if they are long, they can contain approximately 1 deciliter. So 3 times the system is pumped through. And then we cleaned the system with these solvent 1, 2, and 3, the thinners 1, 2, and 3, and then took out samples. And on the next slide, you will see that we sampled after 5 deciliters, after 10 and 15. And then we did a visual inspection of how clean the thinner is afterwards. So, and if you take out every deciliter, then you have, as we see here, then a control series. And you can see that we need more than 1 liter, so 10 deciliters in order to have a clean, at least visually clean system. So up to deciliter 16 here, we have a more transparent liquid at the end. So just, that was the same. So just to show you some of the results that is at least visible. So we had 2 types of paint, one white and one red, and we used the solvent 2 and 3 respectively, as same nomenclature as Mikael's solvent 2 and 3. And if we look at the red setup, because that's more clear in the pictures, even if the white ones are, if you look at them in real, you see a difference. But here, series 3, which is then cleaned with solvent 3, and we have a series 4 with solvent 2. So if we compare then after 5 deciliters of rinsing, you have a somewhat clearer or more transparent washing liquid after that with the solvent 3, and this 2 vials in the middle then is after deciliter 10. Same here, it's even more clear than for the solvent 3, and after 15 deciliters you see a clear difference between the materials, which is then it verifies what we found out in the smaller lab scale tests, that the solvent 3 seemed to be more efficient than solvent 2. And this we did more than 1 time, so to say, so that we have done some repetitive testing, and the difference remained even after that. Yes, Janne, do you want to add something to this, or?
I think you have included the main parts. I'm quite satisfied.
Otherwise, actually, we will continue then with Circam, and you will tell us about how to recycle solvents then. Now we have been looking at the efficiency of them, but how can we recycle all the liters of thinner that is used?
Yes,
So-
and and I will do this presentation. My name is Jon Tillander, and I'm the R&D manager at Circam. And for those of you that don't know us, so we are located in Vargön, near Vänersborg. So first, a little bit about us. We are a green tech company that specializes in recycling solvents from different industries. And here on the picture, you see our site. We have a permit for up to 20,000 tons of hazardous waste. Annually. And for now, we are the only multi-purpose company that does this recycling of solvents. So that's we can change the picture now.
Change slide, yeah.
Slide.
Yes.
So here's the workflow that we have been doing here in the BioCleanPaint project and normally do in all our projects. So first we get some samples from a customer or a partner, and then we do the lab testing of that solvents. Normally we get some information about what will it contain, and in this project we knew that it's thinner that has been in the paint systems. First we do GC or GCMS to see what the samples contains. And we always check the water contents because, as you have seen here before, water and in many solvents aren't that good. So you have to check what levels are. And we also check non-volatile substances to see how the residue will look like afterwards and how much that isn't solvent is in the samples. Then when we do the comparison between the virgin, we also we check between when we do the lab scale tests. We always want to have some samples of the virgin thinner to see what we want to get to, and compare that with a lab. Almost always we do a lab distillation, and what we have done in this project to see if we or do that, and then we compare with the virgin thinner results to see how it looks. So that's the first. In this project we have used 250 to 5,000 milliliters to do our distillations, but could be other techniques too, but mainly the distillation in this project. When we are done with the lab analysis, we go to a bigger pilot scale, as we call it. And this is to check in a bigger scale to see if it's the results from the first step is could be trusted. As a third stage, when the second stage are done and finished, we and the customer sets up an agreement to go into agreement and and saves. This is just to save some CO2, and hopefully this will be profitable for all both parts and the environment. But as you can see, I've written here, the first stage here is just included in this BioCleanPaint project, and the other two something that comes after.
Yes.
And we can take next slide. So here is a little bit of what we have done, but as you have seen before, we have some different types of waste materials or thinners, and it could contain alcohols, ketones, acetates, and other aromatic compounds. And you have seen the 3 different solvents that is mainly used here. And in the lab, you can do the distillation with or without vacuum, and we have used to do it without vacuum. There's pros and cons with both, but with vacuum you could get lower boiling points, and then probably be more there will be less energy consumptions, and you will not get that high temperature of your equipments. As you can see, as in the pictures below to the left, we have one waste we got from the project, one of the types, and we did a recycling, and to the right of that we have what came out, transparent and good looking sample. And now I don't know how big your screens are, but the first you see the recycled thinner first up to in the upper chromatogram. You see you have the main parts. There is 1, 2, 3, 4, 5, and those look quite similar to the virgin thinner. Then you have some small peaks in the chromatogram up in the recycled thinner, but as you can see, there is not much more of other solvents in this case. That's good.
It doesn't say here, but I think we also had a quite high amount or percentage of recycled
materials, I will get to that.
So to say. Sorry, I thought.
But that's good to know.
Yeah.
And why it contains more in the recycled thinner? Why it's more peaks there? Is because mainly of the paint pigments and the paste pigment, paint pigment pastes contains some. Usually they contains the same solvents as in the thinner, but could also contain some more type of solvents, and those solvents could be as efficient to clean, but yeah, you have to be aware of that there could be some issues if there is some kind of solvent that doesn't fit with some equipment. Yeah, we could take next slide to our conclusion here. This solvent recycle maintains a good quality and can be reused, and the recycling rate at our part is 80 to 90% in this case. There could be other type of thinners and such that have lower or higher, but this is what we've seen in this project. And the energy consumption, according to the lab test, has shown quite low kilowatt hour per the recycled kilo of thinner, but it can vary when looking at different substances of the solvent that it contains. And for the LCA that we will look on soon, you will see that this is a great CO2 saving for all the companies that uses it. So instead of letting it go to incineration, that's good. As you know, I mentioned 80 to 90%. The other thing that is left goes to incineration, but yeah, that's better than 100%. So thank you. And
yes, thank you. Any
questions now or later, maybe?
Or both. That's fine, since we're not so many in the meeting, I think.
Exactly.
Or if not, we will, as you said, Jon, jump further to the core results, one must say, the life cycle assessment. What happens then if we change to a non-fossil based material, or if we do recycle our thinner after use? So Anna-Karin, you will tell us about how the LCA is performed and what we found out.
Yes, thank you, Charlotte. First of all, I would like to acknowledge my colleagues Torun and Uniben, who has performed this work. They are our LCA experts. We also have Uniben here in the audience today, who can answer some complex questions that I cannot answer. I'm a chemist by training, and I have been practicing LCA for around 4 years. And I just want to send a message that if you are working within research and development and are not familiarized with LCA, take the chance to get basic knowledge, because it can really help you in your work. So the aim of the study was to evaluate the climate impact of conventional fossil-based and bio-based cleaning liquids for paint shop equipment and distribution systems based on the ISO standard for LCA of these 3 different cases that has been presented. And the key objective was to identify hotspots along the value chain, assess the climate impact mitigation by transitioning from fossil-based to bio-based cleaning liquids. We call it liquids here, but it's the same as the thinner, you could say, as was introduced by, presented by Scania earlier on. And also to compare different end-of-life options, especially the incineration versus recycling. So maybe, Charlotte, you should help me here.
Page. Yeah.
Let's see, I forgot to take the control. I will try here if I can. There we go. Okay. So we have 3 different case studies. And when it comes to the LCA here, because we have different functional unit, the function unit is a way of assessing, using for comparing different case studies. And we have different function units here due to the amount, but also the different formulations. However, we have been using 4 different scenarios within each case studies that can be compared. So the 4 different scenarios are the fossil-based cleaning liquid with incineration at end of life. We have fossil-based cleaning liquid with recycling at the end of life. And then we have the bio-based cleaning liquid with incineration at end of life. And finally, bio-based cleaning liquid with recycling at end of life. So you can shift. Thank you. Next one, I can say. So the goal and scope is to evaluate the climate impact of the conventional fossil-based and novel bio-based cleaning liquids. We focused on 3 different actors in the automotive industry that has been partners in this project. And the assessment is based on the ISO standard for LCA. The system boundaries are from cradle to grave, from raw materials to disposal. We also included sensitivity analysis to evaluate the influence of selected parameters and methodological choices. And the result has not undergone a third-party review, meaning that it should not be added into, for example, marketing materials and so on. Next one, thanks. So if we briefly look into a holistic perspective of the system boundaries, they vary a little bit between the different cases, but this gives you at least an overall picture. And Scania presented their process in the beginning. So for the incineration, we have considered the production of the thinners or the cleaning liquids and the upstream processes. In the use phase, we have been considering cleaning the paint equipment with the cleaning solution or the liquid. And we have also assumed 10% emissions to air. So 90% of the waste cleaning liquid was going to incineration. And for the next one, Charlotte, the recycling system boundary for the recycling. We again start with the production of the cleaning liquids and its upstream processes. And in the use phase, we have been cleaning the paint equipment. Also here, we assume 10% loss to air and 90% went to recycling. So 90% recycled cleaned liquid was transferred back to the user then. And 10% went for incineration. So the next one, Charlotte. Thanks. And the recycling process that was used, it was presented by Sir Kim here earlier. So the waste cleaning liquid was first filtered to remove the paint or the solid part, which was sent to incineration. And then the liquid was distilled and the recycled cleaning liquid was sent back then to the user. The next one, thank you. So the functional unit here that we have been using is how much cleaning liquid that was used for one painted vehicle component, either a cab or airplane. And the reference flow to fulfill the functional unit varied for the 3 cases, and therefore they should not be compared. But the climate impact was also calculated per kilo of cleaning liquid used. That will be presented later on here. The next one, thank you. And of course, we have been doing some assumptions here. For example, no energy use for the cleaning processes, pumps and air pressure was included. The same reference flow for both the fossil-based and the bio-based cleaning liquids was assumed per case. And the same transport distance for the fossil-based and the bio-based cleaning liquid was assumed. And the recycling process was based on the lab scale testing of Circum for the reference cleaning liquids, and where the same process was assumed for the bio-based alternatives that has been modeled here at an industrial scale. The same electricity use was assumed in all 3 cases. All air emissions during the use phase were accounted for as carbon dioxide emissions. So the share of air emissions was based on estimates from the collected data. And the next one, thank you. So here come some of the results from the different cases. And just to show a little bit how to interpret this, on the y-axis we have the climate impact, is kilo carbon dioxide equivalent per painted component. And in the first scenario, we have the reference cleaning liquid going to incineration. In the next one, we have where it's recycled. And then in the third scenario here, we have the bio-based cleaning liquid going to incineration and recycling. The blue here color is the production of the cleaning liquid. The red is the use phase, and the yellow is transport, and the gray is incineration. And then we also have the recycling, which are similar colors, unfortunately, here as the production of the cleaning liquid. And then we have the total here. And as we can see, the main contribution when it comes to the reference, the cleaning liquids based on fossil-based for incineration is the production of the cleaning liquid and also the incineration. So in summary, you could say that for recycling the cleaning liquid, the climate impact was lowered by around 76%. However, going to the bio-based alternative lowered the climate impact with 72 to 93% compared to the reference with incineration, where the best option was bio-based cleaning liquid with recycling. So as we can see, if we compare here a little bit, is that moving towards bio-based formulations or chemicals that are bio-based and also working on recycling in a closed-loop system, we can lower the climate impact. We can go to the next one. Thank you. And here we can see similar trends. I was thinking I'm not digging into the details, but in this case, we have a longer distance between the paint shops and incineration facilities or recycling facilities, and therefore the transport has a little bit of a larger impact here. But still, the highest impact is coming from the production of the cleaning liquid here in the reference flow, where we have the fossil-based liquid with incineration. And as a second dominant contributor is the incineration then. Thank you. We can go to the next one. And also here in the third case, we see similar trends, that the most dominant contributor is the upstream processes or the production of the fossil cleaning liquid and the incineration of the fossil-based cleaning liquid. And the lowest impact is where we use bio-based and where we are recycling the waste liquid. So the next one, thank you. Maybe. So for the key finding, recycling and reusing fossil-based cleaning liquid in a closed-loop system can reduce the climate impact by 75 to 79%. Replacing fossil-based liquids with bio-based options lowers the impact by 64 to 72% with incineration at end of life. It was compared with the incineration scenario. And the hotspots for fossil bio-based liquids, the production was accounted for 45 to 58% of the total climate impact, and incineration contributed to 37 to 40% of the climate impact. And hotspots for the bio-based liquid then was still the production of the cleaning liquid, but since we could kind of neutralize, you could say that the carbon dioxide that is emitted during incineration can be compensated for the uptake of the plant growth. The transport has a quite higher contribution here, 23 to 53% of the climate impact. And then next one, please. So key takeaway, increasing recycling to use resources more efficiently and transitioning to bio-based alternatives are key measures for climate mitigation. However, other impact categories such as toxicity, water use, land use, etc. should be considered in the next step to avoid shifting the burden from one impact category to another. With that said, we can see here that the climate impact can be lowered by using the bio-based chemicals, but it still needs also to be considered sustainability of the process as such. So we don't see a higher impact in another impact category. Thank you.
Thank you, Anna-Karin. Then we'll come to the question part actually, because this was a lot of information in a very short time. So I guess some of you have questions. I hope so at least, but maybe you don't have them now. But let's just, I'll try to be quiet for a few seconds and then let someone. Yes, we have one hand, Mayengo.
Yeah, thank you so much, everybody, for the presentation. But I have some questions for Anna. You talked about bio-based alternatives. Can I know some examples of the bio-based alternatives? Like she said, like Charlotte said, it was a short presentation, but a detailed one. Maybe we missed out on the examples of the bio-based alternatives.
Should we go back maybe to? You mean what type of bio-based
exactly
solvents there are?
Yes.
Anna-Karin, you're muted.
I'm talking to myself here. I'm sorry. Yeah. If it's okay to share, we didn't really know. That's why we didn't really specify it. But we were using for the novel bio-based liquid here that we have been comparing with, it's based on ethyl acetate and ethanol.
Or did you mean the source of the bio-based? Was the question regarding what source of bio-based?
Yeah, because when she talked about like really bio-based, I was thinking it was like a really bio-organic or something like that, not like so much about more of a chemical, you know?
No, it was chemicals. It was only that we used the bio-based sourcing for producing the ethanol and the ethyl acetate.
Oh, okay.
So it's the same solvent, so to say, but the source is bio-based instead of fossil.
Okay. And then I think I have another question to Sir Kem when he talked about.
So for the key finding, recycling and reusing fossil-based cleaning liquid in a closed-loop system can reduce the climate impact by 75 to 79%. Replacing fossil-based liquids with bio-based options lowers the impact by 64 to 72% with incineration at end of life. It was compared with the incineration scenario. And the hotspots for fossil bio-based liquids, the production was accounted for 45 to 58% of the total climate impact, and incineration contributed to 37 to 40% of the climate impact. And hotspots for the bio-based liquid then was still the production of the cleaning liquid, but since we could kind of neutralize, you could say that the carbon dioxide that is emitted during incineration can be compensated for the uptake of the plant growth. The transport has a quite higher contribution here, 23 to 53% of the climate impact. And then next one, please. So key takeaway, increasing recycling to use resources more efficiently and transitioning to bio-based alternatives are key measures for climate mitigation. However, other impact categories such as toxicity, water use, land use, etc. should be considered in the next step to avoid shifting the burden from one impact category to another. With that said, we can see here that the climate impact can be lowered by using the bio-based chemicals, but it still needs also to be considered sustainability of the process as such. So we don't see a higher impact in another impact category. Thank you.
Thank you, Anna-Karin. Then we'll come to the question part actually, because this was a lot of information in a very short time. So I guess some of you have questions. I hope so at least, but maybe you don't have them now. But let's just, I'll try to be quiet for a few seconds and then let someone. Yes, we have one hand, Mayengo.
Yeah, thank you so much, everybody, for the presentation. But I have some questions for Anna. You talked about bio-based alternatives. Can I know some examples of the bio-based alternatives? Like she said, like Charlotte said, it was a short presentation, but a detailed one. Maybe we missed out on the examples of the bio-based alternatives.
Should we go back maybe to... You mean what type of bio-based
exactly
solvents there are?
Yes.
Anna, Karin, you're muted.
I'm talking to myself here. I'm sorry. Yeah. If it's okay to share, we didn't really know. That's why we didn't really specify it. But we were using for the novel bio-based liquid here that we have been comparing with, it's based on ethyl acetate and ethanol.
Or did you mean the source of the bio-based? Was the question regarding what source of bio-based?
Yeah, because when she talked about like really bio-based, I was thinking it was like a really bio-organic or something like that, not like so much about more of a chemical, you know?
No, it was chemicals. It was only that we used the bio-based sourcing for producing the ethanol and the ethyl acetate.
Oh, okay.
So it's the same solvent, so to say, but the source is bio-based instead of fossil.
Okay. And then I think I have another question to Sir Kem. When he talked about, there is a graph that was talking about the recycled and the virgin. I think it was about like the RMS, something like that, analysis.
Jeez, yeah. Let me go back. Few slides, maybe I should. Here, right?
Yeah. Because it shows like the recycled thinner has some, it's good with around 90% to 80% of the recycled substances. But then my question is, how have we thought about maybe what is going to happen over and over? There is this point that maybe he talked about like the particles, the smaller particles around, I think it's between 11 to 12 something. We have some smaller particles there. So I was thinking if we recycle and recycle, how effective is the process going to be if we still get more other particles within the process, and then how effective can we work towards that?
You mean around 11, 12? Those in this chromatogram? You mean? Yes. Yeah. Those aren't particles. It's other solvents with a higher retention time. So it could build up, and then as we have 80 to 90%, if we say 90%, then normally the company will have to get it up to 100% with a top up, and you have to over time you will have to see over time if you just keep on recycling it. You may have to do this top up part a bigger, or you have to start with a new virgin thinner. That depends on how well it works for the customer.
Okay.
Viola, this is Joachim from Circum. May I ask you which company you represent?
Representing Scania. Thank you.
Scania. Okay.
Yes.
Thank you.
Great. Any other questions? on any of the content. Or comments from the rest of the project team. Anyone wants to add something before we close for today?
Maybe I should raise my hand.
No, that's fine.
I was thinking what could be, I mean, it's a lot of results that you have generated during this project. Could it be possible to make like a summary a little bit, for example, about the functions? I don't know if you looked into costs, like a table or something, and with the LCA to see a little bit like an overview somehow. I don't know. Where you tested in lab and pilot scale, for example.
Yeah, we will try to summarize, of course, in a like a short version somehow. So we still have some weeks left to do that. But yeah, and I mean, this is, as you say, we have done the LCA, we've done some lab tests, but it's small pieces of a puzzle. Then of course we have the rest. I mean, as you said, also the LCA.
So here we have been normalizing the results to 1 kilo of cleaning liquid, meaning that, well, thank you. So here we have been normalizing the results to 1 kilo of cleaning liquid, meaning that, whoa, okay, we take the next one. We skip this one, I think. Yeah, we skip this one.
Why?
I was thinking, I see that we kind of showing. I don't know what happened there.